Yeah, it's weird how that works. I don't understand
Yeah, I remember too, but just saying I used mechanical pencil on Scantron tests for like 10 years.
it. Oh, too.
And so I feel like it's close enough that maybe it would work.
So something must be said in the middle of what you just
Did you start doing it?
yeah, I gotta put it off after put it back on, walk home, and then go to bed. Yeah, I'm back in.
Try like zipping it up and just like rub your pencil on it.
Where it gets
Zip that bottom part up too.
I think it gives it like a extra slippy thing. I don't know.
Yeah, just like right on like here. Ah, dang. That's what happened before.
Unbelievable. Oh, John, before, okay, I need your guys' information about the studying class update. Do you have your laptop with you that I can just take a picture of, or did you not write it down?
We didn't have to study that yet.
I know, but I just usually. So if you've got some, I guess it's mine is 0.01.
It is 0.0.
So I don't even do anything.
Yeah.
So, thanks for coming and investing your time. What should we cover?
Why does movies have a star by it?
Because I like it.
Okay.
So, we done this, right? Did I share recordings? Okay, good. It's more important than lectures.
Or
So-
recordings of the lab.
Yes.
Oh, yes, yeah.
So you are ready. Not ready to present right now, but you have all the information.
Yes.
Good. Commutation of operators in numeric representation. Okay, so now it's about 5, and I'll try to be quick. So go along the list for John. So you do remember, or I may hope that you remember, that computation of position momentum will be Planck constant. And if each operator is a matrix, it will be, if we have operator for x, operator for p, then it will be constant multiplied by the unity matrix. And right now it is for John, right? You also do remember we covered in the lecture then that if you have wave function as function of momentum, then you get wave function as function of position, and opposite Fourier transform forward and backwards. If you do have an operator as function of momentum, then you need to apply two integrals in order to convert operator in position representation and backwards. So where it is implemented in the code. So please look through your emails from last lab and then recall sub_d. If you are receiving a couple hundred emails per day because of the ads, I can quickly resend it.
So for the double integral, why is the e to the ix or ix momentum or hr, why is that not negative?
One negative, one positive.
Okay.
Because Brian can't.
I'm sorry, what are we looking for?
Who?
The code that we did last time.
Oh,
Can you access it?
well, I mean, I had it saved on my.
Okay, if it's saved, then you are safe. Good. So I'm opening the code and looking through the make it a little bigger. So one thing that we didn't discuss last time was wave vector, which is the same as momentum with precision up to Planck constant. Since here our Planck constant is 1, it is just same as momentum, and it spans over the same number as for grid points for position, but it starts from negative and goes to positive, so it's around 0. So to cover both positive and negative. And f of t is first Fourier transform. So basically here we are going backwards from position representation to momentum representation. And in the momentum representation, momentum operator is diagonal and consists of values of momentum. So zeros away from main diagonal, and then minus delta p plus delta p plus 2 delta p minus 2 delta p. So it covers all discretized values of momentum. Same as position operator in position representation. So it's like diagonal matrix with all values of the independent variable. And then if we express Hamiltonian in momentum space, for free space it will be just momentum squared. And I want to get to yes. Okay. This is probably one of the toughest parts of the code. So John is suffering at most. Everyone feels easier. What does it mean if we implement this thing practically? So we are trying to replace any integration with multiplication. So if we replace these two integrals with multiplication of matrices, then there will be a matrix for a operator, where indices will correspond to values of momentum, and then we need a matrix that will represent this exponential, where one index corresponds to position and another to momentum, and both of them are placed into the exponential. So, and we have it like matrix, and here this similar matrix, but in the inverse. Matrix minus 1. P prime. And here it will get A with indices x prime in discrete space.
So using the matrices removes the need for the integration?
Yes. So if we want to get element corresponding to value x here, and instead of p it will be only one delta p there. The element that converts represents part of this matrix will be this one. If we want element corresponding to different value of momentum is 2 delta p, it will be just number 2 here, which is equivalent of putting a power here. Right? And if you go further escalating, it will be just number n. So this little r is our elementary part of exponential, like divided by number of points, and then we are taking this elementary thing into the power corresponding to indices for both position and momentum. So if this is done correctly, this W operator will be implementation of Fourier transform. And then if you want to convert from momentum representation into X representation, it will be W W prime. Whew. So why we need it? Why we torture each other with this stuff? Because this definition of momentum is much more precise than the one that will be introduced by Morgan, that we were showing here. The one that Morgan will likely show on Monday is much easier conceptual to understand, and there is nothing wrong with it. But the one obtained through this Fourier transform is gives better precision. Okay, so we are done with conversion of operators between momentum and position. Thank you for being brave and selecting it. Commutation of operators in numeric representation. So size px. Okay, size hop for x operator 200 by 200. So we do have right now px is momentum operator in coordinate representation, and x is position in position. Mesh hop x hop new figure mesh x operator. So it is a diagonal matrix with everything is zero except main diagonal, where it escalates linearly, right? So it's x operator in x representation. What is the px? Okay, it's absolute value, or better, let's do imaginary, because it should have imaginary unit. So if it would be momentum operator defined as we were spending time last week, and as I hope Morgan will represent, it will be, so it is a matrix with almost zeros everywhere, and there are some differences. So in the old-fashioned definition, it will be 1, 1, 1, 1, 1, minus 1, minus 1, minus 1, and 0 in the center, right? It's when it was a really big advantage, big breakthrough when we agreed how to represent matrices through operators. And this is an example of such matrix. But in addition to like a little 1 and minus 1 in here, there are vanishing terms as far as we go away from the diagonal. And this is obtained through this double Fourier transform. Okay? Now, if what we are doing is correct, or at least not very malignant, the operator should match this property. So I would be doing it as plotting x operator times px minus px times x operator. So I'm very intrigued to see. Okay. What is good that it is not 0, but the deviation from 0 could be I would expect, if everything is correct, that on the main diagonal it will be just 1, and everywhere else it will be 0. If it is not this way, it means that what we do is not absolutely correct, that we still have something to explore. Is there a chance that I have missed the something important in the real part? And you're very welcome to practice these things. If you have already downloaded, no, for real part is even worse. Oh, no, it should be X operator. So something is not ideal with these operators. They are they may give some reasonable results, but we are not 100% sure they do not pass the quality test. So X3. So there is one more alternative definitions of the momentum operator, and whoever presented, I think it is John, and partially I also selected alternative methods for dynamics. So you may look into help and demonstration of the method and find what this function is. I'm really interested to learn it from you. But if we use this third way of defining momentum, see what happens. Real part of the commutator is absolutely zero, and if you look for imaginary, there is something of the order of 1 near the main diagonal, and then zeros almost everywhere outside. So this version of defining momentum operator is as much reliable as possible. So if you are presenting this subject, what are you doing? You're doing these things and showing images and explaining to the best.
So,
yes?
how many of them do you want shown?
It's how many will be convincing for yourself, and how many you can fit into 4 minutes.
Good question. Okay.
Right? So done with commutation of operators. So it's again boring and abstract, but it is an important fundamental if ever you will generate some results for true research based on this code. A critical reviewer will say, how can you believe that what you are doing is correct? Or did you check what's the level of precision, the level of trustability? And you can check, well, I did try that this equation partially fulfills. Okay, modeling quantum dynamics of electron. Initial conditions, Gaussian. We did it last time, right? We have all the materials. Alternative methods to compute quantum dynamics. I think that it is the last boring thing. Thank you for being brave in selecting this subject. Okay, so I keep walking through the code, and the stuff here, P2, X3, it is a momentum square operator, again with this function that I'm very looking forward to learn about from John and Alyssa. And then we need CHEM, well, before and then. So G is 0, we can forget it, but it is basically momentum in the X representation times momentum in X representation over 2 mass, which is kinetic energy, and then diagonal of the V operator, which is set to 0 in every application except those 3 that will be represented by Yongu. Right? You change the potential and run the code. You selected the last 3. Right?
What is that?
You did select the last 3 topics for presentation.
Yeah, I did. It was
Good. Yeah. And then this Hamiltonian is plugged into expression for evolution operator. Good. This is based on the definition of momentum that was done as John will teach us in 5 days, right? If the momentum is alternatively defined through this tuplets, then there is a CHEM the third. So it is different representation of Hamiltonian and different representation of evolution operator. So there will be alternative ways to compute dynamics, and if they both are correct, they will generate coinciding results in everything. If there is an error in either both or one, they will start to diverge.
Is that shown like on a graph? Like, is that a figure that?
When you see this moving figure, there are actually 2 wave packets.
Oh, okay.
And they, if we select very small dx and very small tau steps, they will coincide in everything. As soon as we become not patient and try to propagate forward with the big steps, error will accumulate and this start to diverge. And basically we are done with that. Let me just once again repeat what we did before. The loop is a sequence of propagations, and propagation of the wave function by method number 2 for this px is here, line 178, and here is the propagation forward by the method 3. So these wave functions are updated each time code comes through the loop, and later on it will be someone else presenting. These wave functions will be used to find observables, store them, and plot. Of course, as for humans, the movie, how the wave packet is going forward, is the best thing. But for actual exploration, for quantifying observations, one needs some observables. Okay, and there is a method number 1 which is very boring. Is momentum squared in momentum representation, and it is only for educational purposes. So if you want to go through the code and tell what it is, you're welcome, but it is of secondary importance, because this so-called first method is applicable only to free space. As soon as we go to any practical problems, like we will be presenting and as we will explore in the rest of the semester, this e-tau will be not useful. So if you are busy or time is limited, leave it as an option.
The third free space one.
First one in momentum space, number 2 in Cartesian space through the double Fourier transform, and number 3 is through this Toeplitz matrix.
Wait, so the Hamiltonian 2, does that work for everything except for the
Let's plot, just explore what it gives. So if I do mesh CHEM2, close, new figure. It doesn't like me. Okay, let's do real. So it's a matrix representation of Hamiltonian in discrete Cartesian space, and I may want to do the same for Hamiltonian 3. And check if I do see any differences, or I can do the subtraction. And tell, well, they are noticeably different. So in numerical representations they're not equal. So it will be not surprised if they give different results. How to interpret this Hamiltonian? It's a square of first derivative, so it still should be large near the main diagonal and should vanish as far as we depart from main diagonal. The definition of a derivative is the same for each range of space, therefore it doesn't change. It's the same pattern as we go further. When we will go forward to describe systems with non-zero potential, the kinetic energy will be added with potential, and if there is a attractive potential, it will drop down in the middle and then grow further. So the main counterintuitive thing is to think of energy as of matrix. Right? Typically, we are considered as either number, or if it is potential energy, it is a line. And here it's operator of energy. And we just need to make a little step in intuitive perception of the things and be not surprised when we see it. It's more important than little technical details. Okay. Modeling, initial wave functions, alternative methods. Done. Discrete representation of wave function in space and time. Steven, I think we did it last time. Right? Normalization of wave function in discrete representation. We also did it last time. So it partially overlaps with initial wave function, where we had the square root of the dx. Size of the simulation cell versus time of simulation. Let me focus. When the code is running, it pops up several windows, right? And one of them look this way, like I don't know, a little slug is going across the screen. So this image, I can probably turn it around, and I will find a way to maybe enhance it to the whole screen later. So this image is replacing the movie. is the best. So I'm just finding best representation. So the color code corresponds to the height of the probability distribution. Originally we have it somewhere in the center, and it is quite localized. As time goes by, the center is moving and the width increasing. So it is like aquarelle figure, aquarelle pattern, right? So the center of this distribution will correspond to average position where our electron will be. And depending on the initial momentum, it will be, if momentum is 0, it will just go straight up, it will not change. If the momentum is high, it will go with larger slope, right? So the question is, what is the maximal value of momentum that the wave packet doesn't hit the wall? So you just take the distance from center to the edge, divide by time of simulation, and get the velocity. And you may want to illustrate what happens if you increase the value of initial momentum. So if we increase it like 6-7 times, Control S. So if you increase momentum, then it will go through the wall several times, which is not a big problem if you are in physics. But if you are doing chemistry, it's too much of going away from localized molecules. So it assumes that we do not have a localized object, but it is a free space with boundary conditions. And without special needs, it's better to avoid such situation. So what's your expectation how this colorful map will look for the situation of large momentum? Can you show it by hands? It's already there. You can run it, or you can just try. So if you increase momentum, so that wave packet will come through several times, and we represent dynamics in axis of position and time as the multidimensional distribution. What did you do? So as time goes by, it goes with some slope. It arrives to the edge and reappears here. And if momentum is very high, then it reappears there again. So it will be a set of stripes like wallpaper. Make sense? Let's check if it was really so. Okay? So you may show it in a couple of values of momentum and explain what does it mean. Okay. So, done, right? Discrete representation, normalization, size of the simulation cell versus time of simulation. You can keep momentum and time of simulation and increase the number of points or increase the dx, and then this repetition, this coming back through the wall will disappear. They just connect. Kristen. Accumulation of expectation values into array of data for the whole trajectory. Let me see what I practice, because it will be. I don't care what you do, but you might benefit of practicing. The code here is the tool to do a little research. Although it is most of the academic learning course, we are mimicking research procedure because science is not possible without research. And the instrument that looks shiny and gives some nice figures is not possible. You cannot put only photograph of your instrument in your report or publication. You need something more quantitative. And as we were going over in the course, the quantitative things that we are getting out of this approaches, techniques, are observables. Like things that can be either computed, calculated by pen and paper, or measured in the real experiment. You have enough skills both in background of this physical chemistry and in programming to compute any observable through this Bryant cat. So the psi2 and psi3 wave functions, which are updated at each step, are sufficient to you take Bryant cat and put any operator in between. But there is a little challenge, and I'll chat for a couple of minutes more, and then we'll go through the formula. The time goes by. At each time step in the loop, we can compute any observable. But when the code is done, we want to have the values of this observable at each time step, at each point. So we can either open file and write their value by value, or we can declare an array or just with running index and fill it with values. Or if we are not sure if power will be on all the time or there will be outage in between, we can dynamically grow the size of a variable. Remember how we were defining the vectors at the very, very beginning? Like if I tell, let's say, x equals 1, 2, it defines minimalistic column vector. And then after this, I can define y equals x, and then 3 in the next line. And then it will take x as a variable and define y as a 1, 2, 3 vector of larger length. So why don't we practice this procedure again and again to accumulate values of an observable? So, what is your opinion? I'm referring it to Kristen because it's your subject. The rest of us may just lean back and relax. At which place of the code would you put the computation of observables and accumulation of their values? Huh? Good. Before the end of the loop or after end of the loop? Huh? Yes. So then it's sufficient. We go through this main loop, and here it's symbolized by this line. Wherever line ends, there will be end of the loop. So we should explore a little further and see what. Well, there are many things, but it's definitely before the end of the loop. So the anytime possible, we try to avoid wave function toward probability distribution, right? So it is here. So probability as psi 3 and conjugated psi 3. And there is the same thing for the method number 2. If we would place an operator in between, it will be a procedure to compute an observable, right? If we do know that our operator for an observable is absolutely diagonal operator, like position, it's rare, it's not always, then instead of multiplying row by matrix by vector, we can just multiply probability distribution by the values of the position. And in the code, it's not most rigorous way, but it's the quickest and numerically least expensive. So you take probability distribution, which is wave function absolute value squared, multiplied by value of x, and then we integrate, right? And we do not need to write dx because square root of dx is hidden in the wave function. And if we have wave function squared, then it will be multiplied by dx, right? So this line 214 is just expectation value of position at specific step of the loop. Here we do accumulation of this position, maybe in form of a row vector. So we take whatever was stored in this variable before, and then add the value of what is calculated at this loop. How to enable this syntaxes and avoid errors? Before the loop, there should be assigning empty space, empty data, empty array for it of zero length. If you look for part of the code right before the loop, you will see several variables declared in this way. And it is not necessary. One can declare arrays of finite lengths and then populate them. It is just done to avoid unnecessary use of the data if suddenly humans become impatient and stop coding in between. Why to populate more data? Okay, so what did we discuss? We discussed the plot probe 3. So it's a probability distribution at the end of simulation. Plot what was the name of this variable? AVGS3. Okay. So, what do we see here? The initial part corresponds to linear growth of the expectation value of position. So this is time steps, this is position. As you expect from Newtonian mechanics, and as we saw in this quantum course from Ehrenfest's theorem, the expectation values often repeat whatever is expected in classical theories. So it grows linearly. But then as soon as it hits the edge, it reappears from the other side. And then repeats the pattern. Which other variables, which other observables we could be interested to compute and deposit and plot? Momentum, yes, we'll do it. And also we did the remember there was a part in the class for uncertainty relation when we computed the width of the wavepacket. In this code, at the very top of the code, there is a variable x var, which sets up initial width of the wavepacket. Okay? But you notice as time goes by, the numerical representation of the wavepacket increases its width. Right? Can we extract it and plot it? So if it would be, if it is free space, if the wave packet doesn't hit the walls, we can do it analytically. We do not need the code. But we want to be universal and apply it to different situations. And in this code, we have an instance when the wave packet hits the wall and re-enters. So probably we need a procedure that does width of the wave packet numerically. What is it? So if you have absolute value squared, and we call expectation value of x will be can we design an equation that will give us width of the distribution? You all know it. I absolutely guarantee. Each single one. Huh?
Oh no, what?
Suppose you are teaching a freshman course and you need to grade 300 participants.
Oh, like a bell curve.
Bell curve, yes. Gauss. But if you have your curve numerically and you want to say procedure to say whether it is narrow or wide. Maybe you're correct, and I just do not know this colloquial term. Let's check the position.
What?
Suppose you do have a function, let's say p of x, and we have a function either with big width or small width. How to construct an equation that will summarize shape of the function into the width parameter?
I'm sure at some point I knew in statistics, but I don't know.
Yes, in statistics, good.
I guess there's a 3 years
So,
ago, like,
the mean value is this expectation value, right?
yeah.
And width is how far the results may deviate from the center.
So percentages or something.
You know, you're talking about range, right?
Yes. So,
There's standard deviation.
correct. Who told this? Oh, you deserve a credit. So, you take independent variable minus expectation value. It will be how far it deviates from center, but it can deviate to the left and to the right. If you do average only of this thing, it will give 0 for most distributions. But if you take absolute value and then do expectation value, which will mean x minus expectation value of x squared multiplied by distribution and then dx. Root means square, or how you put it? No, square root. Repeat your smart word.
Standard deviation.
Standard deviation, yes. And quantum theory and statistics do not conflict. One can apply the same equation in here. I don't know why I was explaining, because it was written here. So you have the expectation value, which we have this x in angular brackets, minus independent variable squared, and then multiply by probability distribution, make summation, which will correspond to integration, right? And variance, because how much the outcome of measurement vary from the central value, right? So we can call it width or variance or standard deviation. So this one, variance 3, is one number at each time we come through the loop. But if you want to accumulate it, we can call it plural, variances. And accumulate it, make this variable longer and longer. Okay? So what if we plot?
So
Yes.
does that actually like make it continue doing that, or make that variance larger? Making it plural.
I've got the question, and do have the answer in my head. I just need to find the right words.
Okay.
Suppose you are in analytical chemistry lab, and you are repeating some experiment with slightly varying initial conditions.
Oh, okay.
And you just make your recordings either in notebook or in Excel sheet. So if you do the experiment once, it will go to one record. If you do it 100 times, you will have
So it's
100
not like
records.
trials of it.
Right, just
okay.
trials.
Oh, okay.
So right now you see that something is not visible for humans, and then it makes a big spike. It's still Kristen. You will be explaining what the spike is. Huh? Why?
I'm just looking at the y-axis.
Because if this wave packet comes to the edge, if we do not obey prescriptions that Steven will teach us, keep momentum small. If you do not keep momentum small, then it will come through the walls. And when half of the wave packet is here, half is there, the width will be equal to the size of the balls. It will be like a non-realistic effect, artifact of the modeling tool. So we shouldn't compute variance if our wave packet is crossing the border. It will be something crazy. So we can either focus on this little range or just redo simulation with smaller value of momentum and then replot this variance. So 0. Control S for saving. WP underscore something. I did change P naught for a smaller value. So now it is a smaller value. The red and yellow lines do not deviate too much, which means it is more or less reliable. And there will be some error, but not too large. So figure, and I redo the plot variances. So it starts at some small value and then it grows quadratically, right? Exactly as you found in whatever class or homework. So for Gaussian wave packet, width grows quadratically. Therefore, product of uncertainty for position of momentum is larger or equal to uncertainties of Planck constant. Good. Let's see where we are on the saving numerical data into files for separate analysis. If I fail to complete everything today, probably I will need to invest part of the Friday lecture so that we complete things. And we do have a seminar speaker for the department coming to the airport in half an hour or 40 minutes, and I'm in charge of meeting. So, saving. What is LS? Alyssa knows.
Yeah, it lists all of the things that you
Yes.
can do directly.
So right now we do have I have the PowerPoint, I have the code, and something I don't know. So we were plotting variances. Who was teaching us how to save data? John or Steven?
Last time or this
Yes,
time?
last time.
I think I may have.
So I want to believe that you were teaching us to type save minus American whatever standard and variances 3. No error message. And now I'm going to repeat the ls command and see what did happen. Now I do have a file called variances, right? So if I will be lucky today, I probably will be able to find this file in the files and open it with either Notepad, which is a little boring. It will be better to open it with Excel if it is. Does it have Excel? there should be so I'm opening this file, and now it is imported into the Excel, and if you know how to plot with Excel, you can do it. You probably do it all the time, right? So saving numerical data into files for separate analysis. Like if you do not like MATLAB and you are used to use Origin or Excel or GNU-plot, you can export data. Calculation of expectation values, position and momentum. Okay. We already did position, but we haven't done momentum. For momentum, it should be, since it is not diagonal, one would need to do the standard definition of the expectation value. Okay, line 238. So, row, operator, column, and just in case normalization. So if px is our trustable momentum that was giving more or less correct commutation, then this AP3 will be expectation value of momentum. I do not know before we plot whether it will be completely imaginary, but I think I skipped grading part of the homework when we were doing matrix elements, but the answers there will be like pi over h bar times imaginary unit. So accumulation these values are a couple of lines lower. So AP3 is accumulated into this variable. So if you want to check what was the expectation value of momentum for this problem, I would do plot AVP3. And likely there will be an error message. Oh no, it has real and imaginary, but the real part doesn't change much. It's 0.41, and imaginary it's 10 to the minus 17. So let's do the real. Transition matrix elements of momentum were imaginary. So with rather high precision up to several digits, the momentum doesn't change with time. How do we interpret it? In free space, there are no forces. Initial momentum stays constant, right? If we do not follow testament of Stephen, if you took too large momentum and the wavepacket will overcome the edge, there could be a splash in the level of momentum because it just approaches are not trustable near the edges. Okay. What else? expectation values of energy and uncertainty of position and momentum. So uncertainty of position we done. Uncertainty of momentum will be doing the same thing but putting momentum in here, right? And you may invest a little time trying to find these variables. And for the energy, because of the energy conservation, which should be maintained, the energy shouldn't change, right? But let's see if you compute it anywhere here. No, okay. Okay, since we do believe that energy doesn't change with time, although it is an interesting thing to check. If you prove that you break energy conservation law, you can try to publish in top journals and either get glorified or it will be immediately rejected. So we do row by column and we do this CHEM, right? So there is, in the current version of the code, I was not putting energy conservation in doubt, and it is computed only once. But we can just type and see what is the value, like E3. So no imaginary part, and real part is 0.1 in atomic units. We may check how it differs from P0 square over 2 mass, and it is, so the difference between these two numbers, one is defined as quantum approach to compute energy, row, operator, column. Another one is just classical values of momentum squared. If it will be 0 width, very precisely localized point charge, they would coincide. But since it is a quantum particle with non-zero width, there are contributions to total energy associated with the width of the particle, with its quantum properties. And difference of this, like this minus this, it will be a quantitative measure of quantum effects. This will be, for free space, it is not as drastic. But if we would take harmonic oscillator, put momentum equals 0, position at the equilibrium, and then find total energy according to classical value, momentum squared plus potential energy squared, it will be 0, and quantum result will give 1/2 of the frequency. It's like 0 point energy. Okay, I think it is sufficient. Merely visualize real and imaginary parts of the wave packet. We did it last time, right? It's hidden. Let me just this little picture where you have real, imaginary, and then the envelope. Next, visualize potential and probability distribution. Distribution. Why there are 3 of them? So visualize any observable. I think it is what we did for Kristen, for her parts. Just finding this accumulated thing and plotting it, and just using a little of intuition to decide to plot on the real or on the imaginary. Typically, all observables that are coming up in the real measurements are real, right? Imaginary is only if we are looking for something exotic. For potential, I will tell it today, even though there is not much time. But I will tell it after starting the stuff for Yungu. Because right now we do not have potential, and as soon as we move here, we will have several. Visualize any observable organization of data, bundling groups of observables. Okay. Right now, probably you're completely tired of this course and all these abstract things. It looks very unpractical. Even you hear some promises of connection to real life, it doesn't look like much of real life. But suppose you finally made up your mind and wanted to use this code to describe something realistic. You're not, as a user of the instrument, you're not going with a screwdriver open and improve it anytime you do measurement. It should work as a black box. Even if it is not very high quality instrument, it shouldn't be reassembled before each individual measurement. And you have seen that when the code is done, it pops up several videos with some dependencies. So basically the code is prepared to already output things that could be typically interested for a beginner researcher, like position, momentum, uncertainty, they're already there. And maybe instead of doing things that Kristen will show, like finding, focusing on one variable, explaining which code generates, we can fabricate, or it's already done, look how it's fabricated, set of commands that will plot most important variables in the organized way, and just learn the way how it is organized. So after we are done with the main loop, you see this figure, several figures, and this subplot commands. Let's just look on what is being generated. So it shows slice of the probability distribution at last time, the expectation value of position, which is expected to grow linearly. And there are 3 lines because there are 3 different methods. And the uncertainty. So we may, and the last thing is this 3-dimensional representation of a movie. I don't know what to say more about it, but just if we are repeating this calculation again and again for either different initial conditions or for different potentials, it's maybe more reasonable to snapshot all this figure, save it into PowerPoint, and then go to the next measurement, and then try to summarize it by your common sense and intuition. if you want to update this parts, there are a couple of commands of formatting, but I'm not sure if you all need them. So if you plot more than one data set, you put X and Y one after another. If you want to change the range, you put initial and final X, initial and final Y. And if you want to have more than one panels, you do this subplot stuff. So if you plan to present on this, you may meditate of what, on your opinion, would be most useful for practical use of this code, and try to create a flow chart of activities, like how to be an efficient user of it. Visualize potential. Did we do movies with this code? So if you didn't, you know how to make movies, right?
Yeah, I figured it out.
Put specific portion of the code at the beginning, at the end, and inside the loop.
Yeah. We have two loops. Do you have to do it for both of them?
No, only for the main loop where the variable named loop is getting through.
Yeah.
Okay. And in the remaining few minutes, you're good. So there is a I think I need just to remove 0 in line 61 and rerun the code. So this is one of the examples where instead of 0 potential, there is a potential representing like each dip corresponds to an atom. So this comp corresponds to a set of atoms, maybe a little piece of crystal, and with electron tries to distribute between them. You may try to do to see how the observables look like and make any conclusions. So instead of moving straight, it distributes over a broader range over each dip. And there is a set of variables that looks very silly, but it is helpful. I think it is called PL and PR, left and right. Yes, it's right here. So it splits the probability distribution onto part between the center and after the center, left and right, and then it makes summation and accumulate this average PL and average P right. The last panel that pops up when the code ends show two lines that look that their summation will give always one. One is decreasing, another increasing. Right? So it is amount of probability stored in the left half and right half of the simulation cell. If you will need to describe chemical reaction, overcoming the barrier, or electron transfer, going from one side to another one, it will be a good measure of the transfer. So line 191. Hello? Привет, Филипп. Очень тебе рад, перезвоню ночью. Сейчас я прямо лекцию читаю.
Хорошо, извините, пожалуйста.
Ну ничего, все. sorry, the way potential is defined is in the, so we were in the line 61. The set of individual atoms is something rather advanced. What we may want to do more practical is to split our space onto ranges, like to mimic the particle in the box, but not with infinite wells, but with finite height of the wells. So in this line, I am setting up a vector corresponding on 3 segments. So x2 is half of the number of units, AB is, so total number of elements will correspond to the discretization size for x variable. And there are 3 constants that defines how tall or low it will be. So let me run it right away, and it will be much easier to discuss after that. So right now you see there are 3 regions. One is a little lower, another a little taller, and another is even more lower. And the dynamics looks immediately very different. So at the last instant of the dynamics, instead of coming through as a whole, part of the wave packet feels this little bump and tries to reflect back. Right? This modification of a code with the bump in between is mathematically not more complicated than the box, but it is more important. The boxes are important for nanostructures. The barriers are extremely important for chemical reactions, because you have a reactant product and a barrier. Basically, with this modification of a code, it is sufficient to make predictions about chemical reactions, and the value of a barrier, you just put right values for these parameters, right? So we start a little lower, then go a little higher, and then even lower. If we change the middle value to something negative by sign and large by absolute value, Control S. This would correspond to the box of finite depth. You have seen that portion of the wave packet passed through, portion of the wave packet reflected, and a little portion was trapped. So it corresponds to like ionized oxidizer does see maybe electron passing through. You know, it traps electron. Right? If we set up the depth of the well even lower, then I expect the larger portion of the incident electron will be trapped. And we can also make it wider, this walls wider and deeper, and then it will correspond to the particle in the box that we did in the class. So what Yonggu is expected to do is try to do these modifications, make screenshots, and characterize them with observables that are being will be introduced by Kristen and Amelia. Tell like what is expectation level, what is the width, try to characterize what is going on. The potential for this little green line that we do need all the time for a scale. So it is potential is stored in the variable v, and inside the loop there should be the instead of plot you can use this command set, and then you have potential that is being plotted again and again. So we do need to plot both wave function squared and potential to qualitatively analyze it as humans. Because if we do not see the potential, it's not clear what is the connection. I'm done. Formulate your questions.
Yeah, I do, but I'm going to ask you first.
Okay. Yep. You are very welcome to stay here if you want to, but I have to depart. I will be very happy to answer questions by emails, and I'm ready to invest part of the Friday meeting into answering these questions.